Saturn's rings look peaceful from a distance. Thin, elegant, almost delicate. From Earth, they seem like a smooth halo floating in silence around a giant planet. But that illusion disappears the moment you imagine being inside them, surrounded not by beauty, but by chaos moving at unimaginable speed. Now picture this. You are orbiting Saturn aboard a small research vessel. The golden planet fills half the sky. Its rings stretch across space like an endless highway of ice and stone. A minor systems failure forces you into an emergency maneuver. Then something goes wrong. Your thrusters misfire. Your trajectory shifts. And slowly, almost gracefully, you drift into the rings. There is no dramatic impact at first. No sudden crash. Just fragments of ice glinting in sunlight, tumbling silently past your window. Some are as small as grains of sand. Others are the size of houses. All of them are moving at thousands of kilometers per hour, each locked in orbit around Saturn. You attempt to stabilize. You try to calculate your relative velocity. But in orbit, everything is falling together. You are not standing on solid ground. You are inside a river of debris that never stops flowing. And every object around you carries enough kinetic energy to destroy a spacecraft in an instant. So what truly happens next? Could you survive among Saturn's rings? Would you collide immediately, drift safely between fragments, or slowly become just another piece of material orbiting the giant planet forever? Tonight, we step inside the rings, not through imagination, but through physics. Before we explore survival, we need to understand what Saturn really is. Saturn is a gas giant composed primarily of hydrogen and helium, with no solid surface beneath its thick, swirling clouds. It is the second largest planet in our solar system, massive enough that more than 700 Earths could fit inside it. Its rings, however, are not solid disks. They are made mostly of water ice mixed with rocky debris, ranging from microscopic dust particles to chunks several meters wide. From afar, they appear continuous. Up close, they resemble a vast, dynamic field of orbiting fragments, separated by surprisingly large gaps. The rings stretch across hundreds of thousands of kilometers, yet in many regions they are only tens of meters thick. That means they are incredibly wide, but astonishingly thin. Each particle follows its own orbital path, moving at tremendous speed under Saturn's immense gravitational pull. Spacecraft like Cassini have flown between some of these ring gaps without collision, proving that parts of the ring system are less dense than they appear. But density varies dramatically from one region to another. Some areas are sparse, others are crowded and chaotic. So if a person or spacecraft were to become lost inside this environment, survival would depend on more than luck. It would depend on velocity, trajectory, position within the ring system, structural integrity, and time. To understand what would truly happen, we must begin with the moment you cross into the rings. The moment your spacecraft crosses into Saturn's rings, nothing dramatic seems to happen at first. There is no wall to break through, no surface to strike. Instead, your instruments begin registering a sharp increase in particulate density. Tiny grains of ice begin striking the hull with faint metallic ticks, each impact barely noticeable but relentless. Outside the window, fragments shimmer in reflected sunlight, rotating slowly as they orbit Saturn. You quickly realize that you are not stationary within the rings. You are moving at orbital velocity along with everything else, traveling tens of thousands of kilometers per hour around the planet. The key danger is not your speed relative to Saturn, but your speed relative to nearby debris. If your trajectory nearly matches the surrounding particles, collisions might be minimal. But even a small difference in velocity, just a few meters per second, can turn a harmless fragment into a lethal projectile. The rings are structured into bands, the A ring, B ring, and C ring, separated by gaps, such as the Cassini Division. Some regions are dense with clustered material bound by subtle gravitational interactions, known as self-gravity wakes. In those denser regions, ice chunks can form temporary clumps, constantly assembling and breaking apart. As your spacecraft drifts deeper, radar begins mapping larger objects nearby. Some are the size of boulders, others as large as small buildings. They tumble slowly, but carry immense momentum. Because everything is orbiting Saturn, you are effectively inside a flattened debris field in perpetual freefall. There is no up or down, only direction of motion. Attempting to fire thrusters is dangerous. Any sudden change in velocity could increase collision risk dramatically. Your best chance is to match velocities precisely with surrounding material, effectively becoming another particle within the system. However, navigation becomes increasingly complex because Saturn's gravity subtly varies across the rings. Gravitational interactions with nearby clumps cause slight orbital perturbations. Over time, even a stable path may evolve into a crossing trajectory with larger fragments. The sunlight reflecting off billions of ice crystals creates a blinding, almost surreal glow. Saturn itself dominates half the sky, its cloud bands stretching endlessly beneath you. Communication delays increase as signal interference from ring material grows. You are not falling into Saturn yet. Instead, you are trapped in orbit within one of the most dynamic environments in the solar system. Survival in this phase depends entirely on precision. The hull must withstand constant micrometeorite impacts. Shields designed for high-speed dust may handle small particles, but sustained exposure increases structural fatigue. Every minute inside the rings is a calculation problem involving orbital mechanics, collision probability, and fuel limitations. The longer you remain, the greater the statistical chance that your path intersects with a larger object. The rings may appear serene from afar, but from within they resemble controlled chaos, governed by gravity and motion. At this stage, you are not doomed, but you are balancing inside a cosmic shooting gallery where physics decides everything. If a collision occurs, its severity depends entirely on relative velocity and object size. Even a fragment just a few centimeters wide can become catastrophic if the velocity difference is high enough. Kinetic energy increases with the square of velocity, meaning that doubling the speed quadruples the destructive force. Inside Saturn's rings, orbital speeds vary depending on distance from the planet. Inner ring particles move faster than outer ones. If your spacecraft drifts radially, crossing these zones, you introduce velocity differences that could reach hundreds of meters per second. A direct impact with a meter-sized ice block at such speeds would release energy comparable to an explosive detonation. Hull penetration would be likely, leading to rapid depressurization. If the impact occurs in a critical structural region, the spacecraft could fragment instantly, scattering debris that would join the ring system. Smaller impacts would gradually erode shielding. Whipple shields, commonly used on spacecraft, are designed to break incoming particles into plasma before they reach the inner hull. However, they are optimized for micrometeorites, not sustained bombardment from centimeter-scale ice. If structural integrity weakens, cascading failures may occur. Navigation systems could fail, thrusters could become inoperable, and orientation control might be lost. Without control, your trajectory would evolve unpredictably. If you were outside the spacecraft during such an event, survival would be nearly impossible. A direct strike from even a small fragment would be instantly fatal due to extreme kinetic transfer. Even near misses are dangerous. Passing debris can generate shock waves through thin ring atmospheres composed of sparse dust and charged particles. Statistically, some regions of the rings are sparse enough that a spacecraft might traverse them with minimal damage, as demonstrated by the Cassini mission during its final orbits. However, Cassini was unmanned and accepted risk levels unsuitable for human survival. Human-rated systems require far greater safety margins. Over time, gravitational resonances with Saturn's moons, particularly Mimas, shape the ring gaps and density waves. These gravitational interactions create rippling structures within the rings that alter collision probabilities dynamically. Therefore, even if initial entry is survivable, remaining inside the rings becomes increasingly dangerous as orbital perturbations accumulate. Each orbit around Saturn slightly modifies your path relative to surrounding debris. Fuel reserves diminish as you make constant micro-adjustments. The environment is not uniformly lethal, but it is persistently hazardous. Survival hinges on minimizing time inside the densest regions and escaping into a stable orbital corridor as quickly as possible. If you were separated from your spacecraft and drifting individually within Saturn's rings, the situation becomes far more severe. Your suit would protect against vacuum and radiation for a limited time, but not against high-speed debris. At orbital velocity, you are effectively another object in the ring system. If your trajectory matches nearby fragments closely, you might drift temporarily without collision. However, orbital mechanics guarantee gradual divergence. Even microgravity interactions with passing objects can slightly alter your path. Unlike near-Earth orbit, where rescue may be possible within hours, Saturn is nearly 10 times farther from the Sun than Earth, and communication delays would span over an hour round trip. Rescue would be improbable unless another craft were already nearby. The psychological impact would be profound. Saturn fills the sky beneath you, its rings stretching like luminous highways in every direction. Sunlight is weaker at Saturn's distance, casting a dim, cold glow over the ice fragments. Temperatures hover around minus 180 degrees Celsius. Your suit's thermal systems maintain internal temperature, but energy reserves are finite. Meanwhile, ring particles continue their silent dance. Some pass meters away, others drift kilometers apart. You might experience long stretches without visible threat, followed by sudden encounters with dense clusters. Even if no collision occurs, orbital drift may eventually send you inward towards Saturn's atmosphere or outward beyond the ring boundary. If drawn inward, tidal forces and atmospheric entry would eventually end survival. If drifting outward, you could become a temporary satellite orbiting within the ring plane, perhaps for days or weeks, until perturbations alter your path. Biologically, survival time depends on oxygen and power supply. Psychologically, isolation at such scale could overwhelm even trained astronauts. There is no sound, no friction, no way to slow yourself except by expelling limited suit gas, which risks destabilizing your orientation further. You would not fall straight down. You would continue orbiting in graceful, silent arcs, indistinguishable from surrounding debris, except for the fragile human life inside. Over time, gravitational interactions determine your ultimate destiny within the rings. Saturn's gravity dominates, but moons such as Mimas and Enceladus and Tethys exert subtle influences that shape ring structure. Orbital resonances create gaps and wave patterns, gradually redistributing material. If you remain intact, you effectively become a temporary ring particle. Your orbit may slowly decay due to interactions with dust and plasma drag, though this process could take months or years. Alternatively, resonance might push you outward into a safer region beyond the densest bands. The rings themselves are not permanent. They are believed to be relatively young on astronomical timescales and may dissipate over hundreds of millions of years. Within that dynamic system, individual objects are constantly shifting. If your spacecraft survives initial impacts, it might achieve a stable orbit within a ring gap. From there, escape would require carefully calculated thrust to match a trajectory, either inward towards Saturn for gravity assist or outward beyond the ring plane. Fuel constraints make this extremely difficult. Remaining stationary relative to ring particles is nearly impossible without constant adjustments. Eventually, statistical probability favors collision. A large enough impact would shatter the vessel, scattering fragments that continue orbiting Saturn as indistinguishable components of the rings. In that sense, becoming lost in Saturn's rings does not mean immediate destruction, but it does mean entering a slow, probabilistic countdown governed by orbital mechanics. Gravity does not rush, it calculates. The final outcome depends on three variables: time, trajectory, and structural resilience. If you escape quickly into a low-density region and execute a precise burn, survival is theoretically possible. If you remain within dense bands, cumulative impacts will almost certainly destroy the craft. If alone, without propulsion, long-term survival becomes nearly impossible. Eventually, orbital perturbations would either send you spiraling towards Saturn's atmosphere or eject you beyond the rings. Entering Saturn's upper atmosphere would subject you to intense heating and crushing pressure as hydrogen and helium clouds thicken below. There is no surface to land on, only increasing density until structural collapse occurs. If drifting outward, you might survive longer, orbiting in the ring plane as a silent satellite. But supplies would run out. In the grand scale of Saturn's system, a human presence is fleeting. The rings would continue their motion, shimmering under distant sunlight, long after your trajectory is forgotten. From Earth, they would still appear calm and elegant through telescopes. No observer would see the chaos within. And that is the truth about getting lost in Saturn's rings. It is not a dramatic plunge onto solid ground, but a quiet entanglement with orbital physics, where survival depends not on strength, but on velocity and calculation. In the end, Saturn does not need to act. Gravity alone is enough.